Our history of space is a collection of triumphant firsts, but it rests upon a graveyard of forgotten missions. This is the story of 33 lost endeavors that nearly reshaped our universe. You will learn about the secret projects and cancelled voyages that came within a breath of altering everything we know. What if a nuclear bomb-powered rocket had flown decades ago? How close did we come to a human gazing upon the clouds of Venus? By the end, you will see the shadow history of space exploration, a parallel timeline of cosmic discovery that was almost ours. What do you believe was our greatest missed opportunity among the stars? That graveyard of lost missions is filled with the ghosts of an era defined by its breathtaking audacity. The early space age was not a slow march of progress, but a frantic, chaotic sprint. In the shadow of the Cold War, two superpowers threw their best minds and vast resources into a single, all-consuming goal: reaching the heavens first. Every public success, from the first satellite to the first human in orbit, was a moment of global triumph. But behind each of these celebrated victories lay a mountain of blueprints for missions that never left the drawing board. These were not mere ideas, they were fully conceived projects, some even partially built, that were ultimately sacrificed. They fell victim to shifting political winds, to sudden budget cuts when a new administration took power, or to simple, brutal technical realities that could not be overcome with the technology of the day. This created a hidden history of space exploration, a web of parallel paths we almost took. One cancelled mission could have sent a probe to sail the methane lakes of Titan decades ago. Another might have established a permanent lunar base by the 1980s. These forgotten endeavors represent roads not taken in our understanding of the cosmos. They are the echoes of a different future, one that was within our grasp, and our journey to uncover them starts at the very beginning, with the first dreams of reaching beyond our world. The grand tour of the solar system almost began with a very different set of travelers. In the mid-1960s, a few brilliant minds at NASA's Jet Propulsion Laboratory calculated something extraordinary. They discovered that a rare alignment of the outer planets was going to occur in the late 1970s. This celestial configuration, which happens only once every 175 years, would allow a single spacecraft to use the gravity of one planet to slingshot itself toward the next. It was a flight path of unparalleled efficiency, a cosmic free ride. The original mission concept, known as the Grand Tour, was born from this discovery. It called for a fleet of sophisticated, large probes, each one a robotic titan packed with advanced instruments specifically designed for this once-in-an-era opportunity. But the ambition of the plan was its greatest vulnerability. The projected cost was staggering, running into the billions of dollars at a time when NASA's budget was being squeezed. Political support wavered, and in 1971, the ambitious Grand Tour program was officially cancelled. The dream of touring the outer planets appeared to be dead. Yet the engineers refused to surrender the opportunity entirely. They went back to the drawing board, scaling down their grand vision into something more affordable. They took existing spacecraft designs and modified them, creating smaller, more robust, and less expensive probes. This stripped-down project was initially called Mariner Jupiter-Saturn, a name that barely hinted at its ultimate destiny. It was only later that these two hardy, simplified spacecraft were renamed Voyager 1 and Voyager 2, the legendary missions that gave us the pale blue dot and the first close-up views of the gas giants were, in fact, a backup plan. The original, more complex Voyagers would have carried different, potentially more powerful instrumentation. they might have returned even richer, more detailed data from the mysterious atmospheres of Jupiter and Saturn and the icy giants Uranus and Neptune. The mission we celebrate as a pinnacle of human achievement was a compromise, a brilliant recovery from a cancelled dream. This pattern, a grand vision scaled back into a legendary success, would become a recurring theme in the hidden history of spaceflight. And it was not the only audacious plan for the outer solar system that nearly was. While the Voyagers were a scaled-back triumph of engineering, another forgotten mission was far more personal and perilous. At the very height of the space race, hidden within the secretive Soviet space program, engineers drafted plans for a journey of almost unimaginable daring. They intended to send human beings on a flyby of the planet Venus. This was not a simple robotic probe. It was a manned mission designed to hurtle a crew of cosmonauts through the inner solar system, closer to the Sun than any human had ever ventured. The plan centered on a modified Zond spacecraft, a vehicle already being tested for circumlunar flights. This specialized ship would carry its crew on a year-long odyssey. Their trajectory would take them swinging past the cloud-shrouded world of Venus, close enough to witness its searing, acid-drenched atmosphere with their own eyes, before using the planet's gravity to fling them back on a return course to Earth. Think of the view from that cockpit window. A cosmonaut would have seen Venus not as a distant point of light, but as a vast, glowing orb filling their vision, its pale yellow clouds hiding a surface hot enough to melt lead. The scientific return would have been immense, with a human crew able to make real-time decisions and adjustments no automated probe of the era could match. But the price of such a spectacle was immense risk. The spacecraft would have to pass through the solar system's most intense radiation belts, bathing the crew in dangerous levels of cosmic and solar radiation for which there was no perfect shielding. Keeping 2 or 3 people alive, healthy, and sane inside a cramped metal can for nearly 400 days presented life support challenges that pushed the very limits of 1960s technology. Ultimately, this breathtaking plan was shelved. The political landscape shifted dramatically after the American Apollo moon landings, and the immense cost and danger of the Venus flyby could no longer be justified. We came within a few years and a handful of political decisions from achieving a milestone in human spaceflight that remains unmatched to this day, a human journey to another planet. This forgotten mission proves that the ambition to send people into the deep solar system was not a future dream, but a past possibility, one that was sacrificed on the altar of practicality. And as one nation dreamed of sending humans to a fiery world, another was designing a probe to dive directly into the inferno. While the Soviet Venus flyby pushed the limits of human endurance, another forgotten mission from the same era aimed to conquer the solar system with pure, unadulterated power. Project Orion was not merely a rocket, it was a vision of interstellar travel born in the atomic age. Imagine a spacecraft the size of a naval destroyer, a veritable floating city built not in the ocean but for the void between worlds. Its engine was as simple in concept as it was terrifying in execution. The ship would eject small nuclear bombs out of its stern, one after another. These devices would detonate a short distance behind the vessel, and a massive armored pusher plate at the rear would absorb the incredible force of each blast. The ship would literally ride a continuous series of nuclear fireballs through space. This was nuclear pulse propulsion, and its potential was staggering. Freeman Dyson, the visionary physicist who championed the project, calculated that an Orion spacecraft could reach Saturn in just 7 months, a journey that would take our conventional probes years. A mission to Pluto was not just possible, it was considered relatively straightforward. This meant that by the early 1970s, we could have had human explorers gazing upon the rings of Saturn, all thanks to the controlled fury of atomic bombs. The project was not just a paper concept. Small-scale models using conventional explosives were successfully tested, proving the fundamental physics worked. But the very source of its incredible power was also its ultimate downfall. The 1963 Partial Test Ban Treaty, a crucial international agreement designed to curb radioactive fallout in the atmosphere, explicitly prohibited nuclear explosions in outer space. This single piece of diplomacy, aimed at making the world safer, effectively pulled the plug on Project Orion. The political and environmental concerns were too great, the imagery too apocalyptic. The dream of a nuclear-powered ark sailing the solar system was shelved forever, leaving us with the slower, more methodical chemical and ion engines we use today. It was a trade-off, a choice for safety and sanity over sheer, breathtaking speed. The ghost of Orion haunts every discussion about advanced propulsion, a permanent reminder of the road we decided not to take. That third rover, Lunokhod 3, remains trapped on Earth, a perfect machine with nowhere to go, while its two predecessors were trundling across the lunar dust, becoming the first remote-controlled robots on another world. Soviet engineers were already building its successor. Lunokhod 3 was not just another copy, it was a significant evolution. It was equipped with superior, high-resolution panoramic cameras designed to send back even clearer images of the desolate landscape. More importantly, it carried a drill. This simple tool would have allowed it to do what no lunar mission had done before: probe beneath the surface to analyze the moon's hidden geology. With its enhanced mobility, it was built to navigate rougher terrain, to climb into small craters and scale gentle slopes that were previously unreachable. The entire rover was completed, tested, and declared flight-ready. It had a rocket waiting, but its launch never came. As the American Apollo program wound down after Apollo 17, the political urgency of the moon race evaporated. The Soviet space program, its own human lunar ambitions faltering, redirected its funding and focus elsewhere. The completed Lunokhod 3 was suddenly a solution without a problem, a masterpiece with no audience. It was placed in a museum where it sits today, a silent testament to a different timeline. This was not a mission that failed, it was a mission that was never allowed to begin. Its cancellation created a knowledge gap that would last for decades. That drill could have told us about the distribution of water ice at the poles far earlier. Its improved cameras might have identified unique geological formations, clues to the moon's violent history that we are only now beginning to pursue. The story of Lunokhod 3 is the ghost of a more continuous, more methodical exploration of our closest neighbor, one that was interrupted just as it was getting more sophisticated. The ghost of Lunokhod 3 represents a mission cancelled by a loss of purpose, but another forgotten spacecraft was a victim of pure financial reality. Meet the Thermoelectric Outer Planet spacecraft, or TOPS. Designed in the early 1970s, this was not just another probe, it was a marvel of engineering built for the long haul. While the Voyager probes were triumphs of clever compromise, TOPS was designed from the outset to be a titan of endurance. Its most revolutionary feature was its brain, a fault-tolerant computer system. This machine was built to think for itself. If a component failed, the computer would automatically detect the problem, shut down the damaged system, and switch to a backup, all without any instruction from Earth. This self-healing capability was meant to give TOPS an operational lifespan of over 10 years, a staggering duration for the era. This resilience made it the perfect candidate for the most ambitious grand tours, missions to the icy giants Uranus and Neptune, and even a journey into the true void beyond Pluto. It promised a steady stream of data from the solar system's frontier for an entire decade. But this advanced capability came with a significant price tag, and TOPS was conceived at the worst possible time. The political will and seemingly limitless funding of the Apollo era were evaporating. NASA's budget was being slashed, and Congress was looking for cheaper, less ambitious projects. In this new fiscal climate, the robust, expensive TOPS was deemed too costly. The program was cancelled, its revolutionary computer and durable design shelved. Yet its legacy did not vanish completely. Engineers salvaged some of its concepts, scaling down the advanced fault-tolerance ideas into a simpler, more affordable system. This scaled-back technology was incorporated into the Voyager probes. It is one of the great ironies of space history. The very spacecraft that replaced TOPS ultimately relied on a diluted version of its genius to survive. Those hardy Voyagers, which famously lasted for decades, owe a part of their incredible longevity to the ambitious, cancelled TOPS program. We got a taste of its potential, but we never saw the full, glorious capability of a spacecraft designed from its very first bolt to be a permanent citizen of the deep. This sacrifice of advanced capability for cost-effectiveness is a recurring motif in our journey through the stars, a constant tension between our grandest dreams and the practical limits of our wallets. Even the most powerful star in our sky has its secrets, and we came within a single decision of uncovering them in 3 dimensions. The International Solar Polar Mission was born from a brilliant collaboration between NASA and the European Space Agency, a plan to do something no one had ever attempted. They would send 2 identical spacecraft on a grand tour of the Sun's polar regions. One probe would swing over the Sun's North Pole, while its twin would simultaneously pass over the South Pole. This was not just about getting a better look, it was about achieving a true stereo view of our star. For the first time, we would see the structure of the Sun's vast heliosphere, the bubble of particles and magnetic fields it blows into space from 2 vantage points at once. This 3-dimensional perspective would have revolutionized our understanding of solar winds, allowing scientists to track storms and eruptions as they evolved and spread through the solar system. It was a complete picture, a symphony of data where we have only ever heard a single note. The European Space Agency built its spacecraft, holding up its end of the bargain. But as the launch date approached, NASA was forced to make brutal cuts. The American half of the mission was cancelled, a casualty of a shrinking budget. The perfect stereo vision was gone. What followed was a salvage operation, a renegotiation of the entire project. The single remaining European probe was launched, but its mission profile was altered. It became the Ulysses probe, a remarkable and successful mission in its own right. Ulysses gave us our first ever look at the Sun's poles, a monumental achievement. But it was a solitary scout, not a coordinated team. It could only be in one place at one time. We learned a tremendous amount about the Sun's polar winds, but we lost the ability to see how those winds connected and interacted across the vast gulf of space. The cancellation of that second spacecraft created a data gap that solar physicists felt for decades. Every solar storm we could only watch from a single angle, every model of the heliosphere that remained incomplete, was a quiet reminder of the stereo vision we almost had. This mission stands as a stark lesson in how international collaboration, for all its promise, can be fragile, and how the loss of one partner can diminish the dreams of all. The search for life on Mars was almost our main mission in the 1960s, before the Viking landers became famous for their own biological tests. NASA had conceived a far more ambitious project, the Voyager Mars program. This had no relation to the legendary outer planet probes. It was a name reserved for a grand assault on the red planet. The plan was as bold as it was simple: use the immense power of the Saturn V moon rocket. This towering vehicle, capable of hurling astronauts toward the moon, would instead launch a duo of massive robotic explorers on a direct path to Mars. Each launch would send both an orbiter and a large, sophisticated lander on a single, powerful rocket. The landers themselves were designed to be far more capable than what would eventually fly. They were to be packed with a comprehensive suite of biological experiments, a mobile laboratory designed from the ground up with one primary goal: to find conclusive evidence of life. This was not a secondary objective, it was the entire point of the mission. Imagine if, in 1971, instead of the simpler Mariner orbiters merely mapping the planet from above, we had already had a robotic laboratory digging into the Martian soil. The scientific payoff could have been revolutionary, rewriting our understanding of biology and our place in the cosmos a full decade earlier. But the political and financial landscape of the time made such a dream impossible. The entire focus of the American space effort was laser-locked on the Apollo program and the goal of landing a man on the moon. There was no room and, more critically, no budget for a second colossal planetary mission. The Voyager Mars program was cancelled, its grand vision sacrificed to ensure the success of the lunar landing. Its legacy, however, was not entirely lost. The project's core objectives were scaled down, its technology and scientific goals repackaged into a new, more affordable program. That program was named Viking. The Viking landers that finally reached Mars in 1976 were magnificent achievements, but they were a shadow of the original Voyager concept. They carried a smaller, less diverse set of biology experiments, and their results, famously ambiguous, left the question of life on Mars unanswered for generations. The forgotten Voyager Mars program represents a road where the search for life was not an afterthought, but the driving force behind a flagship mission, a path where we asked the universe's biggest question with our greatest tools, only to be told we had to wait. That same audacious Soviet spirit that dreamed of a Venus flyby also set its sights on the red planet. The TMK was a direct and daring response to the American moon landings, a project designed to reclaim the high ground in the space race by accomplishing a feat even Apollo had not attempted. This was not a plan for a landing, but for a crude flyby of Mars, slated for as early as the 1970s. The concept was a masterpiece of orbital mechanics. The TMK spacecraft would not fly directly to Mars. Instead, it would first slingshot around Venus, using the planet's gravity to bend its trajectory toward the red planet. This Venus-Mars double play made the mission duration just over 2 years, a difficult but seemingly manageable time frame compared to a direct flight. Imagine the view from that small, cramped capsule. 2 or 3 cosmonauts would have become the first humans to see 2 alien worlds up close. They would have watched Venus recede as a brilliant, cloud-shrouded globe, only to have Mars slowly grow from a red star into a cratered, rust-colored disk hanging in the blackness. They would have seen its polar ice caps and dark surface markings with their own eyes, decades before a robotic rover ever trundled across its soil. Yet, the price of this spectacular vista was a journey fraught with peril that pushed 1960s technology to its absolute breaking point. Keeping a crew alive for 700 days in the void was the primary obstacle. The ship needed a completely closed-loop life support system, recycling every drop of water and every breath of air, a technology that was still in its infancy. Then there was the radiation. The crew would be exposed to years of cosmic rays and solar flares, far from the protective bubble of Earth's magnetic field. Shielding heavy enough to protect them would have made the spacecraft impossibly massive, and perhaps the most unpredictable challenge of all was the human mind itself. How would a small team cope with the profound isolation, confined in a tiny metal habitat for years, with Earth reduced to a mere pale blue star? These were not simple engineering puzzles, they were fundamental barriers to human existence in deep space. The TMK program was ultimately shelved because these challenges proved too great to overcome with the technology and resources of the time. It remains a haunting what-if, a mission that would have forced us to confront the psychological and physical frontier of long-duration spaceflight a full generation earlier. We chose the Moon, but we almost reached for Mars. The Martian rover's spirit and opportunity were triumphs of engineering, scouring the red desert for signs of past water. But their success created an even hungrier appetite for answers. What if water was not the only ingredient? What if life itself had once stirred in those ancient, damp soils? The answer was waiting in a mission that never left Earth. The NASA Astrobiology Field Laboratory was conceived as the logical, thrilling next step. This was not just another rover, it was a mobile biochemistry lab, a robot geologist with the soul of a biologist. Its primary mission was to go beyond the surface, to places no instrument had ever reached. It was designed with a powerful drill, capable of boring deep into the Martian rock, far below the surface, sterilized by harsh ultraviolet radiation and cosmic rays. Down there, in the protected subsurface, the secrets of Martian life, if they ever existed, might still be preserved. This laboratory on wheels would have collected those pristine samples and analyzed them inside its own sterile, contained body. It was equipped to look for complex organic molecules, the building blocks of life, and for subtle chemical or mineral patterns, called biosignatures, that are notoriously difficult to produce without biological processes. This was our most direct and sophisticated attempt to answer the profound question, did life ever arise on another world? The mission was fully designed, a real project with a target launch date. But then, earthly realities intervened. Other Mars missions, magnificent in their own right, began to experience budget overruns and delays. The colossal cost of developing and launching the Mars Science Laboratory, which would become the Curiosity rover, consumed available funds. In the difficult triage of spaceflight budgets, the future had to be sacrificed for the present. The Astrobiology Field Laboratory was cancelled in the late 2000s, a casualty of financial pressures within its own family of missions. Its cancellation did not just delay another rover, it postponed a focused, deliberate search for life by more than a decade. We are only now, with missions like the Rosalind Franklin rover, beginning to approach the specific capabilities that the Astrobiology Field Laboratory was designed to possess years ago. That forgotten laboratory represents a specific, advanced tool for answering one of humanity's oldest questions, a tool that was fully conceived and within our grasp, only to be set aside. The search for our cosmic neighbors was forced to wait, not because the science was uncertain, but because the money ran out. The dream of finding another Earth was almost pursued not with a single eye, but with a coordinated choir. The European Space Agency's Darwin mission was an astronomical symphony waiting to happen. Its design called for a flotilla of 4 independent telescopes launched together into the deep quiet of space. They would not operate alone, but would fly in a precise, choreographed formation. Their combined light would be funneled into a central hub, creating what is known as an interferometer. This technique effectively gave Darwin the resolving power of a single, gigantic telescope far larger than anything we could possibly build and launch. Its singular, breathtaking purpose was to do what no instrument before it could accomplish: directly image a pale blue dot orbiting another star. It was not designed to see alien cities or surface details, but to capture the faint, telling glow of a small, rocky world. Then it would perform the ultimate analysis, breaking that world's light into a spectrum to read the chemical fingerprints in its atmosphere. Darwin's instruments were tuned to hunt for specific biosignatures, the atmospheric gases that, on our own planet, are undeniable signs of life. The most promising of these is the simultaneous presence of oxygen and methane. These two gases are highly reactive and quickly destroy each other. Finding them together in an atmosphere suggests something or someone is constantly replenishing them. Detecting this combination on a distant world would have been the most profound scientific discovery in human history, a strong, if not conclusive, indicator that we are not alone. But the engineering required was as immense as the potential reward. Keeping 4 free-flying telescopes perfectly aligned, with their positions controlled down to a fraction of the width of a human hair over distances of hundreds of meters, was a staggering challenge in space-based precision. As the technical hurdles mounted, so did the projected costs, until the mission was deemed too complex and too expensive. Darwin was officially cancelled in the 2000s, a casualty of its own magnificent ambition. This cancellation created a decades-long gap in the most critical search of all. While we have since discovered thousands of exoplanets indirectly, we still cannot directly image and analyze the atmosphere of an Earth twin around a sun-like star. Darwin was our first real blueprint for that ultimate discovery, a lost opportunity that forced the quest for life elsewhere to take a slower, more indirect path. NASA's own answer to this cosmic question was waiting in the wings, a project of equal ambition and parallel fate. The terrestrial planet finder was not one mission, but 2 distinct and brilliant concepts vying for the chance to find another Earth. The first design mirrored Darwin's approach, a fleet of smaller telescopes flying in tight formation to create a virtual giant eye. The second concept was a single, massive coronagraph telescope, an instrument with a sophisticated internal mask designed to block out the blinding glare of a parent star, much like you might use your hand to shield your eyes from the sun to spot a distant airplane. By removing that overwhelming starlight, the faint, precious glow of a small, orbiting planet could finally be isolated and studied. The goal for either version was unequivocal: to not only detect rocky worlds in the habitable zone, but to analyze the chemical composition of their atmospheres for signs of life. For years, the terrestrial planet finder sat at the very top of NASA's official roadmap, a stated destination for the next great leap in astronomy. It was the logical next step, the tool we needed to transform exoplanet science from a game of indirect inference into a direct, detailed census of other worlds. But the roadmap and reality soon diverged. The immense technical challenges of both designs came with equally immense price tags, running into the many billions of dollars. At the same time, NASA priorities were forcibly redirected toward completing the International Space Station and sustaining the aging Space Shuttle fleet. These colossal, ongoing projects consumed the agency's budget and attention, leaving little room for new, expensive astronomical flagships. The terrestrial planet finder was quietly, indefinitely postponed, its funding funneled elsewhere. The consequence of this decision, when viewed alongside the cancellation of its European counterpart Darwin, was profound. In the span of just a few years, the 2 most advanced and capable missions ever designed to directly hunt for life on other planets were both shelved. This dual cancellation did not just delay progress, it created a strategic vacuum in the search for habitable worlds. It demonstrated with brutal clarity that even the most profound scientific quests are not immune to the gravitational pull of budgetary constraints and shifting political winds. The grandest goals in astronomy require not just brilliant engineers and visionary scientists, but also a sustained and unwavering commitment from the society that funds them. We chose to maintain our foothold in low Earth orbit, and in doing so, we willingly postpone the chance to learn if we have neighbors. While America prepared to send 2 astronauts to the lunar surface, Soviet engineers devised a more solitary and starkly minimalist alternative. Their lunar lander, designated the LK, was a capsule of pure function designed for a single cosmonaut. It was dramatically smaller and lighter than the American lunar module, a necessity dictated by the limitations of their giant N-1 rocket. This created a mission profile of profound isolation. One person would have to pilot the delicate descent, navigate the treacherous landing, and conduct the entire surface exploration alone, with no partner to double-check systems or share the moment. The psychological weight of that solitary walk would have been immense. After planting the Soviet flag, that lone explorer would have had to re-enter the lander, perform all the systems checks, and launch back into lunar orbit entirely alone, with only a distant voice from mission control for company. It was a mission built on sheer courage and absolute trust in automated systems, and the hardware was not just a dream. Several LK landers were actually built. They were tested successfully in Earth orbit on multiple occasions, proving that the lander itself was a viable, flight-worthy machine. The entire lunar program hinged on one piece of technology that consistently failed: the colossal N-1 rocket. This Soviet behemoth, the largest rocket ever built, suffered 4 catastrophic launch failures, each one a fiery explosion that destroyed the launch complex and with it, the hope of a Soviet moon landing. The capable LK lander never got its chance to fly. It remains one of history's great ironies, a perfectly good spacecraft that was stranded on Earth by the failure of its ride. Had just one N-1 flight succeeded, the story of humanity's first steps on another world would have been entirely different. Instead of the collaborative, 2-person excursions of Apollo, we might have witnessed a single, silent figure from the East, a lone representative of an entire ideology, bouncing across the desolate plains of the Moon. That solitary narrative, a testament to individual bravery over teamwork, is the ghost story of the lunar race, a path that came within a single successful rocket launch of becoming our reality. The immense power of a nuclear reactor was almost harnessed for a voyage to Jupiter's mysterious, ice-bound moons. This was the promise of the Jupiter Icy Moons Orbiter, or JIMO, a spacecraft that would have dwarfed every probe that came before it. Conceived under NASA Project Prometheus, JIMO was not designed to make a brief flyby or a short orbital tour. It was built around a small nuclear fission reactor, a power source that would generate vastly more electricity than the meager trickle from solar panels or radioactive batteries used by previous outer planet missions. This abundance of power was the key to its revolutionary capability. It could operate powerful, energy-hungry instruments for years on end, and most importantly, it could run an ion propulsion system. This efficient engine would have allowed JIMO to perform a tour of the Jovian system unlike any other. It would not just swing past the moons, it could enter stable orbit around Europa, then fire its engines to leave and enter orbit around Ganymede, and then do the same at Callisto. It would have been a permanent resident of that distant realm, spending months or years at each world, methodically mapping their frozen surfaces and probing their deepest secrets. The primary target was the hidden oceans. JIMO would have carried a powerful radar sounder, an instrument that could peer through miles of ice to map the subsurface layers of Europa and Ganymede. It would measure the depth and salinity of these alien seas, searching for the thermal vents and chemical environments where life might just survive. Its other instruments would have analyzed the faint atmospheres and complex surface chemistry of these worlds with a precision we can still only dream of. But the very ambition that defined GMO led to its downfall. The engineering required to safely operate a nuclear reactor in space and to manage its waste heat and radiation was phenomenally complex. The projected cost ballooned into the many billions of dollars at a time when NASA was committed to completing the International Space Station and returning to the Moon. Faced with these staggering technical and financial hurdles, the agency made the difficult decision to cancel GMO. The vision of a nuclear-powered explorer was set aside in favor of smaller, more affordable, solar-powered missions like the upcoming Europa Clipper. While Clipper is a magnificent spacecraft, it cannot match the sheer endurance and power that GMO promised. That forgotten orbiter represents a different class of exploration altogether, a leap to a true, long-duration presence in the outer solar system that we are still, decades later, working to achieve. It was the moment we almost graduated from sending postcards to establishing an outpost. The Moon's heart holds secrets we have barely begun to understand. While orbiters map its surface and rovers analyze its soil, the deep interior remained and still remains largely a mystery. One mission, conceived not with gentle drills but with brute force, promised to change that. Japan's Lunar-A mission was built around a simple, violent, and brilliant idea. Instead of a soft lander, the spacecraft would carry two bullet-shaped probes called penetrators and fire them into the lunar surface from orbit. These were not delicate instruments, they were scientific spears, engineered to survive a high-speed impact and bury themselves deep into the regolith. Once embedded, they would spring to life, becoming a network of advanced seismometers. For the first time, we would have listening posts planted directly into the Moon's crust, feeling for the subtle vibrations of moonquakes and the faint tremors of meteorite impacts. This data would have allowed scientists to map the Moon's internal layers with incredible precision, revealing the size and state of its core and unraveling the history of its formation. It was a classic high-risk, high-reward scenario, a bargain-priced mission that promised a revolutionary scientific return. But the very tool that made it so innovative also led to its downfall. The penetrators themselves were the problem. Engineers struggled for years to ensure these sophisticated darts could withstand the immense G-forces of their own violent arrival. Every component, from the solar panels to the delicate seismometer inside, had to be tested and retested to survive a crash that would obliterate a conventional spacecraft. After more than a decade of development delays and technical hurdles, the mission's window closed. The main spacecraft bus, the mothership that would have carried the penetrators, aged out of its operational lifespan while sitting in a clean room. In 2007, Lunar-A was officially cancelled. The penetrators never got their chance to strike. This cancellation left a critical gap in lunar science that persists today. We have models and theories about the Moon's core, but Lunar-A would have given us facts. It represents a path of aggressive, minimalist exploration, a reminder that sometimes the most direct route to an answer is also the most dramatic. The ghost of Lunar-A is the echo of a seismic thud we never heard, a vibration that would have told us exactly what lies at the center of our closest celestial companion. The promise of a nuclear-powered tour of Jupiter's moons was a dream of immense power, but another forgotten mission offered a different kind of grandeur, one of serene, multi-faceted exploration. Saturn's giant moon Titan is a world shrouded in a thick, hazy atmosphere, a place where rivers of liquid methane carve valleys into a landscape of water ice. It is the only other world in our solar system with a complex hydrological cycle, a frigid, alien mirror of our own planet's weather. To truly understand such a place required more than a simple flyby or a single lander. It demanded a coordinated fleet, The NASA Titan-Saturn system mission was conceived as that ultimate expedition, a three-pronged assault on the Moon's mysteries. The plan was breathtaking in its scope. A sophisticated orbiter would have circled Titan, mapping its hidden surface with powerful radar and peering through its opaque orange clouds. But the true marvels were the two robotic explorers it would deploy. One was a Montgolfier, a hot air balloon designed to float for months in Titan's dense, calm atmosphere, drifting on the alien winds and studying the complex chemistry from above. The second was a dedicated lander, built to settle upon the shoreline of one of Titan's vast methane lakes, potentially even floating on the liquid itself to directly sample its composition. This trio of spacecraft would have worked in concert, providing a simultaneous, holistic view of a prebiotic world. The orbiter would provide context, the balloon would analyze the atmosphere, and the lander would touch the very stuff of the alien seas. We would have witnessed for the first time the full cycle of an alien climate, from methane clouds to methane rain to methane rivers flowing into methane lakes. It was the closest we have ever come to mounting a full planetary exploration of a world so fundamentally strange, yet so hauntingly familiar. Despite being ranked as a top priority by the scientific community for years, the mission's immense cost and complexity became its undoing. The finite pool of funding for flagship missions was ultimately diverted to other monumental projects, the over-budget James Webb Space Telescope and the increasingly expensive Mars Rover program. The Titan-Saturn system mission was quietly shelved, its grand vision sacrificed. Its legacy, however, was not entirely lost. The core idea of mobile exploration on Titan was scaled down, repackaged, and reborn as the Dragonfly mission. This remarkable drone will soon take flight on Titan, an incredible achievement in its own right. But it is a single explorer, a solitary helicopter in a vast world. The forgotten three-pronged mission represents the comprehensive understanding we almost grasped, the symphony of data we traded for a single, brilliant melody. We will still explore Titan, but we will do so with one set of eyes, not three. Venus is a planet that devours spacecraft. The few Soviet Venera landers that successfully reached its surface are legends of engineering, each one transmitting data for mere minutes before succumbing to the crushing pressure and scorching heat. But what if one of them had been built to last? The Venera-D mission was that exact ambition, a design for a lander that would not just survive but endure. This was not intended to be another brief visitor to hell, but a determined resident. Its goal was to operate on the surface for hours, a lifetime in that infernal landscape. Engineers designed it with more robust electronics and advanced cooling systems, all to buy precious time. With that extended life, Venera-D would have conducted far more complex chemical experiments, analyzing the soil and the corrosive atmosphere with a precision its predecessors never possessed. It might have finally determined the exact nature of the mysterious pancake-like rock formations seen by earlier landers, or unraveled the complex chemical cycles that churn within those yellow clouds. But the mission was caught in an endless cycle of redesigns and political turmoil. The collapse of the Soviet Union drained the funding and institutional will needed to turn such a complex blueprint into a functioning machine. Venera-D never progressed beyond the drawing board, a ghost of a more resilient explorer. Its cancellation meant we lost the chance to take the next logical, audacious step in conquering the solar system's most hostile surface. We proved we could land on Venus, but we abandoned the far greater challenge of learning to stay there. That same quest to find other worlds demanded a map of unprecedented precision. The NASA Space Interferometry mission, known as SIM-LIGHT, was designed to be that cartographer for the cosmos. Forget simply detecting planets, this spacecraft would have weighed them. Its mission was astrometry, the ancient science of measuring the precise positions and motions of stars. But SIM Light would perform this task with an accuracy that bordered on the unbelievable. Using a technique called interferometry, it would combine the light from two telescopes separated by a 33-foot boom, creating a virtual instrument with the resolution of a telescope larger than a house. This gave it the power to measure the tiniest wobbles in a star's position. Think of a star like our Sun. The gravitational tug of an orbiting planet, even one as small as Earth, causes the star to perform a minute rhythmic dance in place. SIM Light was so sensitive it could detect that dance from hundreds of light years away. It could measure a shift in a star's position equivalent to seeing the thickness of a coin on the surface of the Moon from Earth. This was not just about finding planets, it was about taking a full cosmic census. The mission would have catalogued the exact distances, masses, and motions of thousands of nearby stars, building the most accurate three-dimensional map of our galactic neighborhood ever made. For the first time, we would know the true scale and structure of our corner of the Milky Way, and by precisely weighing the planets it found, it could tell us which were dense, rocky worlds like our own, and which were gaseous giants, identifying the most promising targets for future searches for life. For years, SIM Light was a cornerstone of NASA's astronomy roadmap, a proven technology in advanced development, but its incredible precision came with a staggering price tag. As costs grew, other major observatories, like the James Webb Space Telescope, began to consume the agency's budget. In a difficult choice, the more foundational but less glamorous work of cosmic cartography was sacrificed. SIM Light was cancelled after years of development. Its loss created a fundamental gap in our knowledge. We are discovering exoplanets by the thousands, but we often do not know their true masses or the exact distances to their stars with the certainty SIM Light would have provided. We are navigating our galaxy with a map that is missing its most critical landmarks. The mission offered us a ruler for the universe, a tool to measure the very fabric of our stellar backyard, and we set it aside just as it was nearly ready to open our eyes. The hunt for alien worlds was almost given a European accent before the name Kepler became synonymous with the discovery of thousands of planets. The European Space Agency was preparing its own trailblazer. Named for Arthur Eddington, the physicist who confirmed Einstein's theory of relativity, the Eddington mission was built with two profound goals. Its primary eye was tuned to the delicate dance of stellar seismology, a field called astroseismology. By observing the subtle pulsations and flickers of a star's light, Eddington would have mapped the churning interiors of suns, understanding their age, composition, and structure from the vibrations rippling through their cores. But its other purpose was even more revolutionary. For years, it would stare unblinkingly at vast star fields, waiting for the telltale sign of a planet. It was designed to use the transit method, detecting the almost imperceptible dimming of a star's light as an orbiting world passed directly in front of it. This mission was scheduled for a 2008 launch, poised to open a new era of astronomy. Yet, just 5 years before its intended flight, it was cancelled. Internal budget reallocations within the European Space Agency forced a difficult choice, and Eddington was deemed expendable. The irony is both profound and poignant. Just 1 year after Eddington was supposed to launch, NASA's Kepler telescope roared into the sky. It used the exact same method, staring at the same patch of sky, and it proceeded to revolutionize our understanding of the cosmos. Kepler discovered more than 2,600 confirmed exoplanets, revealing that planets outnumber stars in our galaxy. It proved that small, rocky worlds like Earth are common, not rare. Every one of those breathtaking discoveries, every statistical revelation about our place in the universe, could have had a different origin. The exoplanet boom, an American-led scientific revolution, was almost triggered by a European telescope. The cancellation of Eddington did not just delay progress, it shifted the entire narrative of discovery. It is a stark reminder that scientific leadership is as much about sustained funding and political will as it is about brilliant ideas. We got the same universe-shattering data, but we lost the chance for a different story, one where the first great census of alien worlds was conducted under a European flag. Even a mission destined for launch can carry the ghost of its former self. The NASA-ISRO Synthetic Aperture Radar, or NISAR, is a remarkable collaboration, a powerful eye in the sky set to monitor our planet's vital signs. But the mission we are getting is a scaled-down version of a far more ambitious dream. The original vision for NISAR was not a single satellite, but a constellation of them. This fleet of advanced radar platforms was designed to work in concert, sweeping the globe with unprecedented speed and detail. Each satellite would have been equipped with sophisticated radar systems, capable of peering through cloud cover and darkness to measure the most subtle changes on Earth's surface. This network would have given us a near real-time pulse on the planet, tracking the sinking of cities by millimeters, the steady creep of deforestation, and the silent flow of glaciers with a constant, watchful gaze. The goal was a complete, dynamic picture of a living, changing world, but the immense complexity and cost of building and launching multiple, large radar satellites forced a difficult decision. The mission was descoped, a technical term for a dream being trimmed back to fit reality. The constellation was reduced to a single, albeit highly advanced satellite. This new NISAR will still be a powerhouse, carrying both L-band and S-band radar to observe Earth's ecosystems and solid Earth. It will provide phenomenal data, a leap forward in our ability to understand climate change and natural hazards. Yet, a single satellite, no matter how capable, cannot be in two places at once. It has an orbital path it must follow, meaning it can only observe a specific location on Earth at regular intervals, not continuously. The original constellation would have shattered this limitation, providing a persistent, overlapping watch that could have captured sudden events, like the immediate aftermath of an earthquake or a volcanic eruption, with a speed and completeness a single satellite cannot match. We are still getting a phenomenal tool, but we lost the simultaneous global perspective that would have truly revolutionized our understanding of Earth as an interconnected system. This is the forgotten promise of NISAR, the more powerful guardian of our planet that was within our grasp, a reminder that even our successes are sometimes built on the foundations of more ambitious, lost dreams. The Soviet Union was not content with merely flying by Mars. They wanted to bring a piece of it home. While NASA was celebrating the success of the Viking landers, Soviet engineers were drafting plans for a feat of engineering so audacious it seems almost fictional today. Their project, known as the 5NM, was a Mars sample return mission designed for a single, powerful launch. This was not a multi-stage plan spread across years and multiple rockets. It was a direct, all-or-nothing assault on the Red Planet. The entire sequence was a ballet of automation, a series of perfect steps that had to unfold flawlessly millions of miles from Earth. A lander would touch down, a robotic arm would reach out and scoop up a precious handful of Martian soil, and then the most incredible part would happen. A small, two-stage rocket attached to the lander would ignite, blasting the sample container up from the Martian surface and into orbit around Mars. From there, a return capsule would navigate its way back to Earth, surviving a fiery re-entry to parachute down with its priceless cargo. This was the ultimate prize, a physical piece of another world for scientists to hold in their hands. The technical challenges, however, were monstrous. The most difficult was the Mars Ascent Vehicle, that small rocket needed to lift off from Mars. Building a reliable rocket engine that could ignite perfectly after a long, cold journey through space and a dusty landing was a problem that pushed 1970s technology to its absolute limit. The guidance systems for the entire automated rendezvous and return sequence were equally daunting. After years of struggling with these seemingly insurmountable hurdles, the 5NM mission was quietly abandoned. Its cancellation meant that the first piece of Mars did not arrive in a Soviet laboratory in the 1970s. Instead, we are now witnessing NASA and ESA embark on a similarly complex endeavor, the Mars Sample Return Campaign. This modern project will use multiple launches, 2 sophisticated rovers, and an entire decade of work to accomplish the very same goal the Soviets tried to achieve with one daring shot. The ghost of 5NM is a stark reminder of a path where we could have held the rust-colored dust of Mars 50 years earlier, a testament to an ambition that was simply too far ahead of its time. The partnership that could have delivered a premier rover to Mars began with a handshake across the Atlantic. The original ExoMars program was a true meeting of minds, a collaboration where NASA and the European Space Agency would pool their expertise to build a robotic geologist of unparalleled sophistication. NASA's role was crucial, providing not just the powerful rocket for launch, but also the advanced design and core instruments for the rover itself. This joint vehicle was conceived as a technological marvel, equipped with a deep drill and a miniature laboratory to search for the complex organic molecules that hint at past life. It represented the next great leap in Martian exploration, a direct successor to the legacy of Viking and a precursor to the curiosity we feel today. But then a familiar specter re-emerged. Back on Earth, NASA faced severe budget constraints, a recurring nightmare for grand ambitions. In 2012, the agency made the difficult decision to withdraw from the partnership entirely. The carefully laid plans were torn up, and the nearly completed rover design was shelved. Europe was left stranded, its flagship Mars mission suddenly without a launch vehicle or a central piece of its hardware. In a scramble for survival, the European Space Agency turned to a new partner, Roscosmos of Russia. This new alliance came with its own set of compromises and challenges. The mission had to be significantly redesigned to fit Russian rockets and systems, a process that introduced delays and added complexity. The consequences of this fractured collaboration soon became starkly clear. The hastily developed Schiaparelli lander, part of the new Russian-European partnership, failed during its descent to Mars, crashing into the surface. The Rosalind Franklin rover, the heart of the mission, was delayed for years, its launch window repeatedly missed. The original NASA-ESA rover was a more capable, more integrated machine, and its cancellation fundamentally altered the trajectory of European Mars exploration. A decades-long delay was introduced into the search for life on the Red Planet, all because the money ran out. This forgotten mission is a ghost of seamless international cooperation, a reminder that the most sophisticated hardware is useless if the political and financial will to launch it vanishes. The threat from the sky has always demanded a response of overwhelming power. Long before the DART mission famously nudged a small moonlet, engineers were drafting plans for planetary defenders of a far more formidable scale. These forgotten concepts were not gentle pushes, they were conceived as sledgehammers. They envisioned colossal kinetic impactors, spacecraft with masses of tens of tons, designed to deliver a blow of such staggering force that it could alter the course of a mountain-sized asteroid, one capable of global extinction. Other designs went even further, proposing the controlled, preemptive use of nuclear devices to either vaporize a section of a smaller asteroid or to generate a massive thrust pulse to nudge a larger one off course. These were not science fiction fantasies, they were serious engineering studies for defending civilization itself. The sheer mass and complexity of these vehicles, however, placed them in a realm of prohibitive cost. Building and launching such behemoths would have required a financial commitment comparable to the Apollo program, a hard sell for a threat that felt abstract and distant. The political sensitivity was equally immense, especially for the nuclear options. Placing weapons of mass destruction in space, even for a benevolent purpose, was a line the international community was deeply reluctant to cross. These formidable barriers of budget and geopolitics meant the grandest defense concepts were shelved. The focus shifted instead to smaller, more affordable technology demonstrators, a path that ultimately led to the successful DART test. But DART was a proof of concept against a tiny, harmless target. We have still never tested our ability to deflect a true planet killer, a rock several kilometers wide. The forgotten large-body spacecraft represent a parallel path where we began developing that ultimate capability decades ago. Our current strategy is built on a foundation of precise, measured force, but we once drew up blueprints for a cosmic guardian of raw, unapologetic power. The blueprint for a permanent moon base was once nearly complete. While the Apollo landers were masterpieces of minimalist engineering, built for short, historic visits, their successor was designed for something far more ambitious: settlement. This was the Altair lunar lander, the crown jewel of NASA Constellation program. Altair was not a simple update, it was a generational leap. Imagine a lander that could carry not 2, but 4 astronauts down to the lunar surface. Its cabin was spacious enough to allow for extended missions, lasting not just days but potentially weeks. This was a machine built for work, for serious science, and for the first foundations of a lasting human presence. It was equipped with an airlock, so astronauts could come and go without having to depressurize their entire living quarters, a crucial feature for frequent excursions. Its powerful engines were designed to land heavier payloads, including the initial components of a lunar habitat, power generators, and rovers. Altair was the key that would unlock the door to the moon, not for a flag and footprints, but for a future. The design process was exhaustive, reaching an advanced stage where engineers had solved countless complex problems, from the descent trajectory to the thermal shielding. It was a real spacecraft waiting in the digital realm for the final command to be built, but that command never came. In 2010, the entire Constellation program was cancelled. The political and financial winds had shifted once again. The vision of a sustained return to the moon was set aside, and with it, the Altair lander was consigned to the archives. The immediate consequence was a strategic void that would last for more than a decade. NASA still had the Orion crew capsule and was developing the giant SLS rocket, but it suddenly had no way to get astronauts from lunar orbit down to the surface. They had a car and a highway, but no front door to their destination. The loss of Altair did not just represent a delay, it represented the abandonment of a fully realized plan. We are only now, with the Artemis program's new lander contracts, beginning to rebuild the capability that Altair already offered. That forgotten lander is the ghost of a smoother, more direct path back to the moon, a path where the hardware for a lunar outpost was already designed and waiting. The quest to understand our own origins led scientists to look not just at planets, but at the ancient, untouched rocks drifting through the void. The European Space Agency's Marco Polo mission was designed for this profound purpose, a direct journey to the beginning of the solar system. Its target was a primitive near-Earth asteroid, a cosmic time capsule left over from the chaotic construction of our planetary neighborhood. Unlike the processed rock of the Moon or Mars, these asteroids are believed to be pristine relics containing the original, unaltered materials from which the planets formed. Marco Polo's mission was to rendezvous with one of these dark, primordial bodies, gently touch its surface, and scoop up a precious sample of that ancient dust. The true prize was not the rock itself, but the complex organic molecules preserved within it, the very chemical building blocks of life. By bringing this material back to Earth for analysis in the world's most advanced laboratories, scientists hope to answer a fundamental question: did the ingredients for life rain down on the early Earth from asteroids like this one? The mission was a finalist in the ESA's Cosmic Vision program, a top contender for flight, but in the competitive selection process, it was ultimately not chosen. Other missions with different scientific goals were deemed higher priority. The opportunity for Europe to lead this specific search for our cosmic roots slipped away. The scientific goal, however, was so compelling that it was inevitably pursued by others. Japan's Hayabusa 2 and NASA OSIRIS-REx missions later executed nearly identical plans, successfully returning pristine asteroid samples to Earth. Their triumphs are a validation of the Marco Polo concept, proving its vision was both sound and achievable. Yet, their success also underscores a lost opportunity. The search for life's building blocks in the rubble of the solar system, one of the most exciting chapters in modern space science, was almost a European-led endeavor, a different narrative of discovery that faded into the shadow history of what might have been. The vast silence between stars was almost broken by a messenger we built on purpose. While the Voyager probes are celebrated for accidentally drifting into interstellar space, NASA once drafted a plan to send a dedicated emissary there on a direct, high-speed mission. This was the innovative Interstellar Explorer, a probe designed not to visit a planet but to conquer the void itself. Its goal was to reach 100 astronomical units from the Sun in less than 15 years, a journey that took Voyager over 26. It was engineered for speed from the outset, using a massive rocket and a slingshot maneuver around Jupiter to achieve a velocity that would make it the fastest human-made object ever launched. This was not a passive drift into the great dark, it was a targeted sprint, and its scientific purpose was just as focused. The probe would carry instruments tuned specifically to analyze the interstellar medium, the thin soup of gas, dust, and cosmic rays that fills the space between solar systems. It would have directly sampled this pristine material, measuring its density and composition without the contaminating bubble of the Sun's influence. For the first time, we would have studied the true galaxy from within, understanding the raw stuff from which new stars and planets are born, but the mission's very ambition sealed its fate. The projected cost was immense, and the timeline for receiving meaningful data stretched for decades. In a world of annual budgets and shifting political priorities, investing billions in a project that would not yield its primary results for a generation was a hard sell. The innovative Interstellar Explorer remained a brilliant concept study, a set of detailed blueprints that never received the formal approval to become metal and circuitry. Its cancellation means we still rely on the aging, fortuitous data from the Voyagers, which were never designed for this specific task. We have a postcard from the edge when we could have had a full research report. This forgotten mission represents a conscious choice we made, a decision to postpone our first deliberate steps into the galactic ocean, leaving the next purposeful leap to the stars for a future generation to attempt. The Moon could have had two nations circling it in the same era. As Apollo astronauts trained for their historic landings, the Soviet Union was executing a different, desperate gamble. Their Zond program, using the sleek L-1 spacecraft, was not designed for a lunar landing. Its mission was more cinematic in its own right, to send human beings on a single, looping journey around the far side of the Moon and back to Earth. This circumlunar flight would have been a monumental achievement, making cosmonauts the first humans to ever leave Earth's immediate gravitational influence and gaze upon the Moon's hidden face with their own eyes. Several unmanned Zond spacecraft successfully completed this exact journey. Zond 5, launched in 1968, even carried a biological payload of turtles and other life forms around the Moon and returned them safely to Earth, splashing down in the Indian Ocean. The spacecraft worked, the flight path was proven, cosmonaut crews were in training, their names assigned to specific missions. The Soviet Union was on the verge of claiming a profound space first, a human circumnavigation of another world. But then, history intervened. Apollo 8 achieved that very feat first, with 3 American astronauts reading from the Book of Genesis as they orbited the Moon on Christmas Eve. The subsequent success of Apollo 11 in landing on the lunar surface was the final blow. The political value of a Soviet flyby, a mission that would now be seen as a distant second to an actual landing, evaporated completely. Sending cosmonauts on a journey that Apollo had already surpassed seemed like a pointless, even embarrassing, risk. The entire manned Zond program was cancelled. The ghost of this mission is one of the most poignant, a historic first that was technologically within reach, but was stolen by the relentless pace of the competition. A Soviet crew never got to witness the breathtaking sight of the entire Earth, a beautiful blue and white marble rising over the barren lunar horizon. We were within months of a completely different narrative for human spaceflight, one where 2 superpowers, not one, had sent their citizens to dance in the Moon's gravitational embrace. The universe builds its greatest wonders behind curtains of dust, and for a while we had a key to pull them aside. The Origin Space Telescope was conceived as a far-infrared eye, a successor to the great observatories that came before it, designed to see the heat glow from the coldest, darkest places in the cosmos. Its mission was to trace the very flow of water from the icy disks around newborn stars to the vast reservoirs in interstellar space, mapping the journey of one of life's essential ingredients across the galaxy. It would have peered into the violent, dusty hearts of galaxies to watch stars being born in real time, and studied the atmospheres of exoplanets in unprecedented detail. This was not just another telescope, it was a machine for watching creation itself. Ranked as a top priority by the nation's leading astronomers, its path to construction seemed certain. Yet, when the time came to translate that recommendation into metal and glass, the project was paused. The estimated price tag, stretching into the many billions of dollars, was simply too high for the initial round of funding. The sheer ambition of the telescope became its greatest liability. We are left with a profound silence where its data should be. Every time we look at a blurred, distant stellar nursery with our current tools, we are reminded of the crystal-clear vision we almost possessed. The Origin Space Telescope remains a set of brilliant blueprints, a ghost of a future where we could have watched planets coalesce from cosmic dust and traced the water that fills our own world back to its interstellar source. A fully assembled scientific laboratory carrying the hopes of a nation plunged back through the atmosphere in a fiery streak. The Mars 96 mission was Russia's grand return to interplanetary exploration after the Soviet collapse, a flagship project designed to prove the nation still possessed its cosmic prowess. This was no simple orbiter, it was a complete survey package, an entire fleet in one. The main spacecraft was equipped to circle Mars, mapping its mineralogy and atmosphere, while its 4 passengers promised an assault on the surface itself. 2 small, hardy landers were built to settle onto the plains and study the local weather and soil chemistry. Even more daring were the two penetrators, spear-like probes designed to slam into the Martian ground at high speed, burying themselves to take the planet's temperature from within. This ambitious suite of instruments was poised to deliver a holistic picture of Mars, from its upper atmosphere to its subterranean heat, a data bonanza that would have arrived in the late 1990s. The mission launched perfectly from the Baikonur Cosmodrome in November 1996, but then a catastrophic failure in the rocket's fourth stage left the entire assembly stranded in a low, decaying Earth orbit. Just days later, the 5 spacecraft, representing years of work and the collective knowledge of a generation of Russian scientists, burned up in a final, tragic light show over the Pacific Ocean and parts of South America. The loss was absolute. Not only did it erase a comprehensive scientific survey, it effectively ended Russia's ability to mount major, independent planetary missions for decades. The timing adds a layer of profound irony, for had its rocket performed, Mars 96 would have likely beaten NASA's, a celebrated Pathfinder rover, to the surface by months. While the world was captivated by the small, charismatic Sojourner rover in the summer of '97, we could have already had 2 stationary landers and a pair of subsurface probes quietly returning a richer, more diverse stream of data. The ghost of Mars 96 is a monument to a different future for Russian space science, one shattered not by a flawed design, but by a single, brutal malfunction in a rocket stage. Even the most iconic perspective of our planet was almost lost to political debate. The story of the Deep Space Climate Observatory begins not with a scientific goal, but with a visionary one. In the late 1990s, Vice President Al Gore envisioned a spacecraft that would do something no other had ever done. It would travel to a special point in space 1 million miles away, a gravitational sweet spot between the Earth and the Sun known as L1. From that unique vantage, it would capture a continuous, real-time, full-disk image of our entire sunlit world. This mission, originally named Triana, was meant to be a daily reminder of Earth's beauty and fragility, a live feed of our shared home suspended in the black void. It was a profound piece of environmental art with a powerful scientific purpose, promoting awareness of our changing climate by showing everyone the planet as a single, interconnected system. But this very ambition made it a target. The mission quickly became politically controversial, seen by some as an expensive publicity stunt rather than serious science. Political opposition was fierce, with critics mocking the idea and questioning its value. In 2001, the newly elected administration cancelled Triana entirely. The completed spacecraft, a sophisticated observatory ready for its journey, did not launch. Instead, it was packed away and placed into storage at the Goddard Space Flight Center, sealed inside a clean room warehouse. For over a decade, it sat there in silence, a technological ghost, a finished masterpiece with nowhere to go. Its original vision of fostering global environmental consciousness was shelved and seemingly forgotten. The mission was only resurrected years later when the National Oceanic and Atmospheric Administration saw a different use for it. They needed a new satellite for monitoring space weather, solar flares, and coronal mass ejections that could disrupt power grids and communications on Earth. The old Triana spacecraft was pulled out of storage, its instruments partially repurposed and rebranded as DSCOVR. It finally launched in 2015, a full 14 years after it was built. Today, it does important work monitoring the Sun, and it has taken some stunning images of Earth, but its primary function is not the continuous, inspirational live feed it was designed for. That original purpose, the simple, powerful idea of a constant, shared view of our planet, was the forgotten mission. We got a valuable weather monitor, but we lost a permanent public mirror for humanity, a daily perspective that might have fundamentally changed how we see ourselves and our responsibility to this fragile blue marble. The concept of a controlled strike against an asteroid was once a fully formed blueprint, waiting only for a launch command. The European Space Agency's Don Quixote mission was not a vague idea, but a technically mature and brilliantly simple plan. It called for a pair of spacecraft named Hidalgo and Sancho to perform a cosmic experiment on a real near-Earth asteroid. Hidalgo was the impactor, a dense, simple projectile designed to slam into the asteroid at tremendous speed. Its partner, Sancho, was the observer, an orbiter that would arrive first and position itself to watch the entire event with a suite of sophisticated instruments. The goal was not destruction but precise measurement. Sancho would analyze the asteroid's composition, structure, and rotation before the impact. Then, as Hidalgo struck, it would record the resulting plume of debris and, most critically, measure the minuscule change in the asteroid's orbit and rotation. This was the definitive test of the kinetic impactor theory, a dry run for saving the world. The data would have told us exactly how much energy is required to nudge a city killer or a continent killer off its course, providing the fundamental physics for any future planetary defense system. Yet, despite its elegant design and clear importance, Don Quixote was never funded for flight. The mission remained an exquisite study on paper, a victim of budget limitations and perhaps a lack of political urgency. The consequence of this cancellation was a delay of more than a decade in our practical understanding of asteroid deflection. The task of proving the technique fell to a different agency, NASA, which successfully executed its DART mission in 2022. While DART was a magnificent success, it was a path we had already mapped out years before. Don Quixote represents the ghost of a European-led defense initiative, a foundational experiment that could have given us the confidence and the data to build a planetary shield a generation earlier. That sweeping vision for human deep space exploration was officially declared just over a decade ago. In 2004, the United States government laid out a concrete path for humanity's future among the planets. The vision for space exploration was not a single spacecraft or a single launch, but a comprehensive national policy. It promised a step-by-step return to greatness, beginning with the retirement of the Space Shuttle and the development of a new crew vehicle called Orion. The central pillar was a permanent return to the Moon by the year 2020. This was not framed as a repetition of Apollo, but as a proving ground. The lunar surface would become a laboratory where we learned to live and work on another world for extended periods, testing the technologies and techniques needed for the ultimate goal, a human mission to Mars. For the first time in a generation, there was a clear, funded, and politically endorsed roadmap stretching from low Earth orbit to the red plains of another planet. This vision gave birth to the Constellation program, which began designing the towering Ares rockets and the Altair lunar lander. Engineers and scientists had a destination, a timeline, and a purpose that stretched decades into the future. The path to Mars was not a vague dream. It was a series of engineering milestones on a calendar. But a national vision is only as stable as the political will that sustains it. When a new administration took office just a few years later, priorities shifted dramatically. The stated goals of the previous plan were re-evaluated, and the immense costs were scrutinized. The Constellation program was cancelled, and with it, the vision for space exploration was effectively defunded and abandoned. The immediate consequence was a strategic void. The clear roadmap vanished, replaced by uncertainty and debate. The hardware that was already in development, like the Orion capsule, was repurposed, while other critical pieces, like the lander, were shelved completely. This created the infamous gap in American human spaceflight capability. where the nation had no vehicle to reach the International Space Station for nearly a decade and no defined destination beyond it. The cancellation did not just delay our return to the Moon, it shattered the consensus on where we were going next. We lost more than a decade of coherent momentum toward Mars, a decade where we could have been building that lunar outpost and testing those life support systems in deep space. The ghost of that 2004 vision is the future we were promised, a future where we might already have astronauts training on the Moon today for the journey to Mars tomorrow. That same Soviet drive that pushed for a Mars sample return also created one of the most advanced and tragic machines in space history. The Buran space shuttle was not a simple copy of its American rival. While it shared a familiar winged shape, its capabilities were in many ways superior. The most stunning difference was its brain. Buran was designed from the outset for fully automated flight, from launch to orbit and all the way through a precise, uncrewed landing on a runway. This was a level of robotic sophistication the American shuttle never achieved. In November 1988, the world witnessed its solitary, ghostly triumph. A Buran orbiter with no one at its controls was launched by the colossal Energy rocket. It completed 2 perfect orbits of the Earth, and then, in a breathtaking display of autonomous precision, it navigated back through the atmosphere and touched down on a landing strip in Kazakhstan, stopping within inches of its target centerline. It was a flawless debut, yet it was also the end. The political and economic collapse of the Soviet Union meant the vast funding required to sustain the program evaporated almost overnight. The Buran, a masterpiece of reusable spaceplane technology, suddenly had no mission, no budget, and no future. The surviving orbiters, including the one that had flown, were sealed away inside giant hangars at the Baikonur Cosmodrome. There they were left to the mercy of the elements. A collapsed roof eventually destroyed one of the pristine vehicles, a slow-motion burial for a program that had reached its peak and then been abandoned. The ghost of Buran is not just a cancelled spacecraft, it is a fully operational system that was used a single time. It represents a parallel path where automated, reusable spaceplanes became the norm for accessing orbit, a road that was open for only a fleeting moment before it was closed off by the tides of history. The sleek, futuristic shape of the X-33 Venture Star looked like it had flown straight out of a science fiction film. This was not merely another rocket design. It was intended to be the true successor to the Space Shuttle, a fully reusable single-stage to orbit vehicle that would slash the cost of reaching space by a staggering 90%. Imagine a world where a spacecraft could take off like a rocket, deliver its payload, and then glide back to Earth to land on a conventional runway, all without shedding a single piece of itself. After a quick turnaround, it would be ready to fly again, just like an airplane. This was the revolutionary promise of Venture Star, a partnership between NASA and Lockheed Martin that aimed to make access to space routine and affordable. The key to this audacious plan was its revolutionary engine, the linear aerospike. Unlike traditional bell-shaped rocket engines that are optimized for a specific altitude, the aerospike was designed to be efficient at all altitudes, from sea level to the vacuum of space. It was a smarter, more adaptable engine that could theoretically provide more thrust with less fuel, but this brilliance came with immense complexity. The aerospike required entirely new manufacturing techniques and materials that pushed the limits of 1990s engineering. Then came the second and ultimately fatal challenge. The vehicle's central liquid hydrogen fuel tank was a marvel of lightweight composite construction, but during a structural test in 1999, it catastrophically failed. The tank, a critical component meant to be both strong and incredibly light, simply could not handle the immense pressures of flight. This single failure shattered the project's timeline and budget. With the technical hurdles proving too great and cost spiraling, NASA cancelled the X-33 program in 2001. A full-scale prototype stood partially assembled, a ghost of a future that never arrived. The cancellation of the X-33 did more than just end one project. It fundamentally set back the entire pursuit of single-stage to orbit technology for a generation. The dream of a fully reusable, airplane-like spaceship was deferred, forcing us to continue relying on expendable rockets or partially reusable systems for decades. We are only now, with modern private ventures building massive new rockets, beginning to close that technological gap that the X-33 tried to leap across in a single, daring bound. It remains the most tangible ghost of a different space age, a silent, sleek spaceplane that promised to open the heavens, only to be grounded by the stubborn realities of physics and funding. That pattern of cancellation has left a permanent mark on our journey. The universe we know today is not the one we were destined to see, but the one we could afford to explore. This relentless pruning of ambition has left us with a thinner, more fragmented understanding of the cosmos. Consider the cumulative delay. We could have confirmed the existence of subsurface oceans on Europa 2 decades earlier with a mission like GEMO, fundamentally reshaping the search for life before the 21st century even began. We might have held a piece of Mars in our hands in the 1980s, accelerating our study of the red planet by a generation. The simple, haunting question of whether we are alone could have been answered with a definitive maybe by the terrestrial planet finder or Darwin, redirecting the entire course of astronomy. Each of these lost missions represents a key piece of data that was missing for decades, a silence in our conversation with the universe that forced scientists to work with incomplete maps and unanswered questions. This delay is more than just a pause. It is a lost generation of scientists who never got to analyze that data, and a public that never experienced those revelations. Our collective sense of wonder was subtly diminished, our timeline of discovery stretched and slowed. Beyond the science, the geopolitical landscape of space was reshaped. The collapse of projects like the joint NASA-ESA Titan mission or the original ExoMars rover frayed the bonds of international cooperation, forcing nations to go it alone or seek less stable partnerships. The cancellation of the Soviet manned programs left America without a competitor, arguably slowing the pace of human exploration for a time. The technological path we walk was also diverted. We chose chemical rocketry over nuclear pulse propulsion, slower probes over enduring orbiters, and single satellites over coordinated fleets. This was not always the wrong choice, but it was a choice, and each one closed a door to a different kind of spacefaring future. The ghost of the X-33 reminds us we could be flying reusable spaceplanes today. The shadow of Project Orion asks if we might already have outposts orbiting the moons of Saturn. These are not just fantasies, they are the echoes of futures that were once on the drawing board, futures that were traded for more practical, more immediate goals. The true cost of these 33 missions is not measured in dollars, but in the parallel universe of knowledge we almost inhabited. These 33 missions are far more than historical footnotes. They are the ghostly echoes of an entire space age that could have been, a persistent reminder that our path to the stars is not a straight line. It is a fragile thread, constantly vulnerable to the shifting winds of politics, the harsh realities of budgets, and the simple, brutal misfortune of a rocket stage failing to ignite. For every Voyager that triumphs, there is a TOPS probe that never got its chance. For every Apollo landing, there is a Soviet LK lander stranded on Earth, a perfect machine with nowhere to go. This hidden history teaches us that progress is not inevitable. It is a choice we make year after year to fund the difficult, to pursue the ambitious, and to look beyond our immediate horizon. Yet within this graveyard of cancelled dreams lies a powerful testament to human ambition. These were not failures of imagination. They were blueprints for wonders conceived by minds that refused to be bound by the possible. They prove our relentless drive to push boundaries, to seek answers to the universe's biggest questions, no matter the cost or the challenge. Let these forgotten endeavors inspire you. The next time you look up at the night sky, wonder not only about the planets and stars we have mapped, but about the parallel universe of knowledge that remains just out of reach. Think of the oceans on Europa we might have already mapped, the soil of Mars we could have held in our hands, the Earth-like worlds we may have already identified orbiting distant suns. The discoveries that change everything are still waiting, hidden just beyond the edge of our current reach. The next great mission, the one that redefines our place in the cosmos, could be the one we choose to fight for today. It is a future we must decide to build. Which of these forgotten missions do you wish had flown? Share your thoughts in the comments and subscribe for more journeys into the hidden secrets of space.